Okay, so to continue the rest of the spectroscopy talk, so I'm gonna start talking about the how do we capture these spectra. So the idea here is that we want to convert the light that we capture from the telescope into spread them out into a sensor, like spreading out peanut butter on bread. So typically, people use what's called diffraction gratings. The ones that we use specifically are called transmission gratings. It's to spread the light. So, give you an example here. We got a transmission grating here. If I shine a light to it, because the way these are shaped, and actually, it's pretty cool physics, is that there's interference based on these grooves so that there are different orders of diffractions are imaged on the other side of the grating. So there are several different orders. So if I shine a light to this type of transmission grating, you see patterns of the light spread out from blue to infrared for each order. So, for example, here, this is how a typical transmission grating is made. There are features here that kind of so that it's evenly spaced, so that we shine a light to it, it'll diffract, and then the angles are dependent on the wavelength. The key here from this formula is that A is the distance. So if the same wavelength and the same order, if I have the same spacing, or let's say I double my spacing, then the angles actually get smaller. So in other words, if I have tighter spacing, then this spreads even more. That's all you need to know about in terms of this formula, how this grading works. So the shorter line spacing, the spectrum is going to spread more. So here's an example. So this is spectra of a calibration neon lamp that's imaged on a full frame DSLR camera. It's 35 millimeter, using a 100 millimeter lens, and the objective lens, the aperture is 58 millimeter. It's a macro lens. So if I have a 50 lines per millimeter spacing grating through transmission in front of the objective lens, this is the actual neon lamp. And also it's been spread out for different orders. You see first order, second order, third order. And it's actually on both sides. So you see for a neon lamp, you see the actual wavelengths actually spread. First order, second order, third order on both sides. This is 50 meter. And I have 100 millimeter, 100 millimeter per 100 lines per millimeter. And you see the more lines, it spread further. And I actually have two of them, and they're different quality. You notice this one, there's actually diffractions diffracted both sides, but there's actually a special type of diffraction grating that's called blazed diffraction grating, where it's designed so that the groove is asymmetrical, so that it's favored to shine one side than the other. So you actually see a lot more photons on this side than this side. I have a 200 lines per millimeter ones. As you can see, it's spread even further. And another one that's 300 lines per millimeter is even further. You see, right here, it's very hard to resolve the individual lines. Right here, the individual emission lines. Remember I told you each element emit in these very discrete lines? These are the lines. So you see, it's kind of, you can make it out. You can definitely make it out when I zoom in, but you can definitely see that even without zooming in a straight line. So you can see the more lines or shorter the spacing, the spreads further. That's essentially that formula in action. So we're going to use this grading technique to create our spectra. There's two techniques that's actually used. One is putting the grading inside, a lot of time inside the optical train. I'll kind of explain that a little further. The other way is that you put the grading outside, called objective grading. And we kind of describe both in our Facebook group. So here's Seestar. Seestar, optically, it looked like this. This is your objective lens, light coming in from the space. This is parallel. So it gets focused by this group of lenses, this triplet, and then it gets bounced by mirrors and then bounced to the sensor here. So instead of looking at that, this is more traditional way of seeing a refractor. The lens here, lights come through here, and it goes in there. Oops, sorry. So light go through here, and then your sensors and stuff here. All right. So that's how lights come in. Our idea now is we want to put the diffraction grading in the optical path so that when the light shines, it diffracts so that the different wavelengths are spread so that we can see it in our sensor. So how do we do that? So the first one is putting grading inside. So we actually can open up the inside box of the Seestar or put something inside in the train of my telescope. Here, denoted by this red rectangle. So you got to put it inside optical path. So this is sealed. So you got to put it inside. You can a lot of people actually put this inside. There are different optics you can put inside the focal plane. And then in that case, you can actually use the slit to do star isolations. Because the lights are concentrated, so you get a lot more signal and you need less space. So that means you have better signal to noise ratio. But because it's so short between the grading to the sensor, the amount of spread, even to have the same angle, the spread's not that far. So that means that they still bunch up pretty close together. So that means you actually have better signal to noise, but you have lower resolution, because to see those lines, you need those lines to be spread out further. Because it's kind of tight, you can fit more of the spectra in a frame. Now you saw before, if I have a full frame camera and a short 100mm optics, I can fit all that into one frame, even for outside. But remember, the Seestar is a very small sensor. It's tiny, so you cannot fit all that in one if you have a very tight grading. I'll explain that a little further. And also, you notice that when the light come in, it's not actually parallel. Remember, the formula for dispersion in grading it's assuming is parallel, so that you get that nice diffraction pattern. But if it's not this way, it's like here it's focusing, there's actually some distortion in the dispersion, so it's not linear anymore. So it's a nonlinear dispersion. All right. So that's first technique. The second technique is called putting the grading outside. In that case, I'm simply putting a diffraction grading outside the lens. Notice the light's coming in parallel. I don't have to put it inside my telescope, but it's coming from outside. It's outside. So I just got to hold it somewhere in my lens hood, so that when light come in, it goes straight to my sensor, and all the diffraction will be spread further and be captured by my sensor. So what does that mean? So first of all, if I want to capture as much light as possible that still have that diffraction dispersion, I need my grading to be big. Before, if I put it here, my grading could be very small. But in here, ideally, your grating should be at least as big as your front objective lens. So you have something smaller, that means you're cutting off the lights coming in. So it's still doable for bright stars and stuff. But if you start capturing some lighter, darker ones, of course you want to use as much of your front lens as possible. So because of this, um, the lights coming in are going to spread further because you have such a, even the same angle of dispersion, because you have such a long distance. So the light spreading the same angle, but have traveled so long, it's spread much further. Because of that, the same amount of light is now spread over a long distance. So that means you're going to have smaller signal to noise ratio because the signal got spread further out. But because it spread so far, you're going to have a higher resolution, because remember those lines before, it's very hard to resolve in a smaller dispersion. But now with this all spread out, I can actually see individual line much better if I can resolve it, if I have enough signal. Now, also because it spreads so far, and because the sensor for Seestar is so small, I need a lot more frames and stitch them to create a full visible range of the spectrum. I kind of mentioned also that because the light's coming in parallel, it fit perfectly in that dispersion formula. So the dispersion is quite linear, very predictable in that case. So those are two differences. So two set of examples. This set of slides kind of represent what's possible right now by our members, Jeremiah and others. They actually put one of the grating inside the optical path, and you can actually see, because of that, it's a lot closer to sensor. So that means I think he's using 100 lines per millimeter grating. So because of relatively wide spacing, and because it's so close to the sensor, he was able to fit the whole the 0th order where the star is, and the 1st order of the diffraction rate of the spectra. So because of that, it's very easy to process. So from here, you can see the whole everything in here. So you can see actually a lot of different stars. So every star has its own spectra. Oops. So here's the other example of that grating inside the cavity. Mentioned before, where Jeremiah was able to do 4 different exposure of different stars, each on its own frames. And from there, he was able to plot the spectra over wavelengths, the intensity of the emissions. So some stars is very hot, some stars are very red and cold. So again, all these are with each of its own frame, so it's quite easy to process, and it's very bright, and you can see a lot of different stars in the neighborhood, and lots of spectrums. Now, these are the second technique where we're using objective lens. These are right here using 200 lines per millimeter, these are analyzer ones. And you can see the spectra now, it's actually quite spread out. Now, this is Sirius, is a very bright blue star. The pattern is very clean in terms of, it's very representative of a lot of hydrogen activities. And these are very good for calibration, in fact. That's one technique to do calibration, stellar calibrations. But again, you can see the spreading of the spectra is very different from when I put the grating inside a cavity. And in fact, here's one I did very early. This is probably a month and a half ago. This is one of the very first experiments I was able to complete using my setup. Again, this is using the 200 line per millimeter grading. And this is actually the emissions measuring the sun spectra, our sun, reflected off Jupiter. So this is in literature what the profile would look like, and these are different absorption lines for the sun and also some of the for the elements on Jupiter. And this is what I was able to capture very early on using that setup. You can actually see the lines here. These are the two lines that corresponding to the, again, very similar to right here. So you can get an idea that I was able to capture even early on the absorption lines for our sun. Again, I'm not sure I kind of mentioned. So kind of give you an idea the how big of the spectrum it covers the sensor. This is our sensor for Seestar. You can see it cover this portion. It covers this part. You can see actually absorption line here and here that correspond to absorption line curve here. So you can get an idea. This one is roughly around this much. So you can see I'll probably need like 4 or 5 frames to capture full visible range of the emission spectra of Sirius. So for a 200 lines per millimeter grading, I probably need to do a mosaic of 5 to capture this full. So definitely not as simple as in terms of processing the spectra, because I need to line them up and process. But you can see the resolution that I can get out of this. And now, because we can actually stack the frames together, in theory, I can get more and more of these signal, higher and higher signal to noise ratio. So, right. And I'll cover the others later. So in this talk, I'll focus just on objective grading. Both techniques are described in our Facebook group, but in this talk, and I mainly focus on the higher resolution because I'm more interested in that, because you can see a lot more phenomena and actually look at things like redshift in terms of determining the speed, because the spectra can actually shift based on how fast it's moving relative to us, and also the rotation of these stars actually will broaden the peaks. So if you can measure the broadening of the peaks, you can actually measure a lot of the physical phenomena. And there's a whole bunch of temporal things I can also describe too. So here I'm going to deep dive in terms of the type of gradings that I've used in the last month or so. I bought 2 different type cheap ones from AliExpress. They're 50 lines per millimeter and 100 lines per millimeter. I have a Star Analyzer 100. They're blazed, and Star Analyzer 200 were blazed. And I just acquired a Thorlab 300 lines per millimeter, 50 millimeter square. It's much bigger than the others because I want to make use as much of the aperture as I can. So I was really looking forward to this, and it's also blazed. Now, blazed again, meaning is that it's shaped so that it give priority to one side of the fractions. So it's more efficient for us to capture and then analyze, because not looking at both sides. We just want to look at one side. So we want the blaze version as much as possible. And I'll kind of give examples of the difference between the two. So these are the suppliers I got from. So again, these 2 are the cheapos from AliExpress. You can get for like $5 to $8. Very, very cheap. The Star Analyzer is around 200, and Thorlab's around 250 or 300. And again, here's the spectra that are imaged on a full frame DSLR. This is a Canon 5D, so it's a full 35 millimeter DSLR imaging on a 100 millimeter, 58 millimeter macro lens. So give you an idea how much is spread based on the line length. Again, this is putting in front of the aperture. So this is objective lens diffraction. So this is 50 lines. You can see the dispersions, and this is 100 lines. you can see this. These are unblazed, so you can see it's equal on both sides. So you swing the energy, all the photons on both sides, and you can also tell how efficient it is because the more energy is on the zeroth order, the less energy goes to the wing. So that means if I want to get as much spectrum as possible, I want as less energy as possible in zero and as much energy here. So you can see the quality where this is okay, but you can see this between the cheap grading from AliExpress and the SA100. This star analyzer 100. And this star analyzer 200. You can see this is the Thorlab 300. You can see even less. So most energy is here. It's also spread out quite a bit further. So you get an idea. And if I do a line analysis and I integrate, this is the Thorlab 300 line one. You can see this is zeroth order, and this is the blue, green, and red portions of the spectra as collected by the sensor. And you can see it resolved really, really well. Again, this is probably 500. Let's say this is around 400 pixels here, and there's probably 15 lines. So you can see the resolution very good. But keep in mind too is that this is my Canon 5D. The pixel size is actually very big. It's like 5, 6, or 7, I forgot, in terms of micron pixels, whereas Seestar uses around less than 2, less than 3. So I'm even get twice the resolution than this when I put it on the Seestar. So you can just visualize how much resolution I can get if I'm able to do that on the Seestar. Now I'm going to kind of go through the design objective lens of the grading. Let's see. I'll focus on the objective gratings, and in here again both are described in our group, but I'm going to focus here how I actually put the grading on the Seestar in the objective grading technique. So I'm going to show you two designs. Both designs serve as a grading holder. It holds the grading. It's a deuce shield, and also as a lens hood, because I image in my backyard, so it's I mean there's a lot of spurious light. So that's how it would look like if I put one of the grading holder in front of my Seestar. So I'm going to show you the video now. All right. So now you know how to make the grading holder. And to give you an example, if you do that, you put that grading, let's say 300 lines per millimeter grading uh, in front of the Seestar, and I have a set up a helium calibration lamp, and I create an artificial star by punching a hole there, and I put it probably as far away as from the Seestar I can inside the house, which is like 70 feet probably. I can focus it so that I can actually here is the spectra of a small portion of that helium lamp. Again, remember these are absorption lines. Well, actually now these are lamps, so these are emission lines from the helium. So these are telling you the different wavelengths that this helium lamp is emitting. And you can see individually how well it resolved in terms of how thin the spectra is. Ignore these wings and saying because this star it's just with a small pinhole that I created on a tape, so it's definitely not a perfect circle. So if I had a perfect small diameter pinhole, I would have really nice lines just all lined up here. So you can kind of give an idea what kind of resolution you can get by having this type of objective grading using a 50 millimeter square in front of the Seestar. And this is the setup I'm going to use to collect the spectra that will generate the stars I sent. Okay, so once you set up your Seestar with that grading in front, um, we're gonna start acquiring those spectral images with the goal that once we collect a bunch of these and in mosaic and then merge it together, you can process this to a point where these are the type of spectra you're going to get. In fact, this is done a while before using the SAR Analyzer 200. So remember I told you that now I'm using the Thorlab 300 lines per millimeter and even a much bigger uh, size, two inch square versus 1.25 circle. I'm going to get more photons and got a lot more signals. So, and because it's 300 lines versus 2, it's going to be even spread out further. So my resolution even better than this. So that's going to be next. Okay.